Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Now that we've gone through the nature of active galaxies and looked at the nature of supermassive black holes that appear in the centers of those galaxies, it's time to look at the largest issues in the universe, meaning cosmology, the cosmological study of the Big Bang and the entire universe. So the first thing we're going to talk about is some underlying assumptions that we have about the nature of the universe before we actually get through all the rest. And the first most important underlying idea is what I call piece zero, is the homogeneity and isotropy of the universe. And so cosmology, again, is the study of the entire universe and the physics, distribution, motions of stuff in the universe and how it evolves with time, what the age, origin, and fate of the entire universe is, and it relies upon the cosmological principle that says that there's nothing special about our location in the universe other than that it's our particular little home. So therefore, we should see that, but now we have two definitions, isotropy and homogeneity. So the principle is that if we have isotropy around any point in the universe with this principle, that means the universe is pretty much the same everywhere. And that's going to color everything we do from here on out. In fact, this is a fundamental aspect of the entire nature of everything, and that includes everything. Homogeneous everywhere doesn't just mean this type of thing is here. It means the laws of physics are the same there. So that tells us that anyone, anywhere, sees roughly the same thing no matter where they look. All right, so to help us with this thing, we are going to start looking at the Hubble Deep Field. We talked about this prior. This was one of the most important images taken in 1996 of taking a huge amount of Hubble time and staring out into space with the Hubble Space Telescope and viewing what can be seen. And this incredibly deep field stares back at us, and we see over 1,500 galaxies of various states and evolution. Some are closer, some are nearer, and this is a very small piece of the sky. But what we can see in this is that the view of the sky shows us that we really just see galaxies out there, so we may actually have something here. All right, we don't live in a special place in the universe. What does that end up meaning? Well, let's look at what we see when we do surveys, such as this is the APM Galaxy Survey, which is looking at the southern galactic pole. If we look around the southern galactic pole, and there's a huge area of sky, like 4,300 square degrees in the sky, this map of about 185 images combined together, all stacked together to make this survey. And they basically, and what was looked at by this particular group, by Maddox et al. In 2003, is they found approximately 20 million galaxies in this area. So where the Hubble Deep Field saw a lot of galaxies inside a very narrow beam, this shows that things roughly are kind of smoothly distributed, except if we look at those kind of webby sort of structures that are in the nearby area. But if we think about the deeper colors, it almost looks the same everywhere. It's almost like you could take a bucket of it and center a box on it, and it'd be roughly the same appearance inside that box, no matter where you put the box on this field. And that's what we call homogeneity. So let's look at the history of the nature of this. And if we go back in time, we find that the universe this concept of the homogeneous and isotropic universe had to take time to develop. In Ptolemy's original formulation of the cosmos, as we saw very, very, very early on, Claudius Ptolemaeus said that if the Earth was at the center and all the planets orbited it and the stars were far out. Well, this kind of gave us an isotropic view, meaning if we're in the Earth, we're in a very special place, the Earth, and we looked out, we see stars in pretty much every direction. Now, this was altered by the idea that you had more stars along the Milky Way than others, so really it wasn't a very good isotropic view. And the planets orbited the sun, they orbited the Earth, They orbited the Earth and went around, but in general, the conceptualization was that the ancient Greeks and many people around there thought that this would be something that is about right, and that's why they drew it using perfect circles, is because while we see some imperfections, they thought that over the largest size scales, it would smooth out, and philosophically, they wished to have it this way. So this was the picture of ancient Greece and ancient Egypt. So when we get to the Renaissance in Europe, in the middle of the 1400s, late 1400s, early 1500s, we find that we see a slightly different alteration of things, getting out into the cosmos, pushing humanity different with Nicholas Copernicus's view of the cosmos with the sun at the center, and then again isotropic based upon the sun's perspective, not the Earth's perspective. So that means that the Earth's perspective is not as important as, say, the sun's perspective. So now we have an idea that we have multiple perspectives. Galileo came along and tried to assert Copernicus' view by saying that the Earth must not be at the center. And one of he used some major justifications when he first looked through the telescope. One of the major justifications, as you're seeing this image, is that he saw the phases of the moon, and by looking closely at the moon with a telescope, you see that the moon has ridges and lumps, and you also see Jupiter has additional starry messengers around them, and those starry messengers are separate stars that orbit Jupiter. And so he posited that if the Earth was moving, it could take the moon with it in just the same way that as Jupiter moves, it takes its stars with it. However, for him, the more important thing was that Venus's phases could not be replicated in Ptolemy's view of the cosmos. They demanded something like Copernicus' view. Now, Galileo, at the same time, was ignoring the work being done by Johannes Kepler, who actually sent him some of his work, but Kepler himself said it was too difficult to understand. And Kepler said to Galileo, look, we can put, instead of circles like Copernicus did, we can use ellipses, and it works really well. Galileo was fighting with the Pope and getting himself under house arrest, so he didn't actually listen to Kepler or read about him or even acknowledge him. But they were roughly coincident. And it ended up that Kepler's view of the cosmos was the correct one. See, Galileo was fully Copernicanized, but Kepler said, well, let's use some ellipses, and it worked. And then along came, using those ellipses, Sir Isaac Newton, who then said, we have that laws of physics are the same. So why does the moon orbit the Earth? The moon orbits the Earth because it's falling towards the Earth, and it has a lateral motion around the Earth. So as it falls, it starts to fall, but then it has a lateral motion whose speed is so great that by the time it would have hit the Earth, it has moved a long ways. So the attractive force of gravity keeps it in a circular orbit. And so he said, well, if that's what's happening, then the Earth is going around the sun by the same principle, and Jupiter is going around the sun by the same principle, and all the stars in the sky are under the influence of gravity. And therefore, all of the laws of physics can be combined into three major laws: the law of inertia, the law of forces, the definition of a force, and the law of equal and opposites. So these ideas allowed to say, well, we no longer need a mystical structure such as a celestial sphere devised by Ptolemy and Aristotle and even supported by Copernicus. All we need is these laws, and they tell us how things move. And what that said is that these laws, if they apply here and they apply there, we're now branching out and applying physical laws to things we cannot get to. And that's interesting. It's really interesting. We're now saying that the laws of physics of the heavens are the same as the laws of physics on Earth. That becomes really critical. And that's what we did. That's how we divided up the world. And I mean, if you go back to the ancient times, back to pre-Ptolemy, if you look at Aristotle's view, Aristotle's entire physics was based on the idea that there were two different realms of physics, one in the celestia and one in the materia. And so they were different. However, Newton came along and finally said, nope, they're the same. All right, this matters a lot because we're going to try to demonstrate the largest size scales of the cosmos. And what do we mean by largest size scales? We don't mean things measured by parallax or proper motion or the Hyades fitting of main sequences to HR diagrams, nor do we even think of getting out to the Large Magellanic Cluster or out to M31, the Andromeda Galaxy, at 10 to the 6th parsecs. No, we don't even think about getting out to M81 or the Virgo Cluster, which is 60 million light years away, or even what we can find with the Tully-Fisher relation that gets us out to 10 to the 8th parsecs, or even supernovae, which get us out to almost 1 billion parsecs. No, we have to actually get out to where our measurements must be measured in redshift, where we measure things on the order of hundreds of millions of light years or billions of light years. That's what we mean by the largest size scales of the universe. And this kind of homogeneity and isotropy only appears on the largest size scales. So when we look closely, we say, what do we mean by homogeneous and isotropic? Okay, a forest looks the same when you're in the middle of the forest, roughly in any direction. That's why it can get confusing to get lost in a forest, because you don't know which way to go, because all the trees look the same. And so your only way, and if it's a cloudy day, you don't even have the sun to help you. If it's a rainy, cloudy day, you better have a trail and you better have a map. And that's all there is to it. Otherwise, north is as good as south, is as good as east, is as good as west, and you can't tell one from the other. That's what we mean by isotropic. The cosmological principle says it's, again, largest size scales. There's no special place. It's homogeneous. Isotropic means there's no special direction. And largest size scales meaning we have a big box that's on the order of 100 million light years or greater. And the two little sketches below show us those to demonstrate the concepts of homogeneity and isotropy. So homogeneity then says, of course, we look at the average density of matter is about the same. So we say, how many counts of galaxies can we do over here? In this box, the average in this box size, say 100 million light years on a side, we get so many galaxies. And if we just change the position of the box and just say, well, if we go over here and make a box that is 100 million light years on a side, then we should have roughly the same number of galaxies. Now we probably will have, 1,000 or so more galaxies or less, but on average, it doesn't matter. The total number of galaxies, it's not like you're going to have 0 here and a trillion over there. That's just not how that works when you get to the largest size scales. And as you can see from the APM Galaxy Survey, there's not really a lot of holes. There are no holes in the galaxy distribution. It's not like, oh, over here, nobody has ever said anywhere, this is the place in the sky where you look to find galaxies, because that's where galaxies are, except because of the blockage by the Milky Way. Everybody says, like, well, if you could look through the Milky Way, you should see galaxies, but no one has ever said, there's no galaxies there, right? It's kind of weird. Nobody's ever said that. It could have been said, that could have been how the world would have worked. The world can work however it wants to, but it worked out that there are galaxies in every direction. The universe is therefore pretty smooth on the largest size scales, but when you look closer, everything looks kind of lumpy, because you know what? A boat is not the same thing as a building, so the universe is lumpy and unsmooth on small size scales. And so the solar system is lumpy compared to the view around the sun in a few light years. But even then, when you get out a few light years, you start to say, oh, there's some big stars and small stars. And you get even further out and you say, oh, there's a galactic disk. You get even further out and you say, oh, there's the local group. And you get out even further and say, oh, there's the Virgo cluster. And it has to get out to the point where you look at superclusters of galaxies before you start to say, oh, now we're starting to get kind of even distributions of superclusters of galaxies. That's what we mean by homogeneity. Isotropy, on the other hand, is to say, look in some direction. Doesn't matter where you look. Start from where you're looking from. Look out in every direction. What do you see? Do you see roughly the same things in every direction? Again, that's not the same thing as a homogeneity. Homogeneity can be homogeneous, but not looking the same in all directions. That is possible, because there could be an innate structure, just like a brick wall, like we saw in the previous. A brick wall is certainly homogeneous because the lay of the bricks. But it isn't isotropic. And let's go back just to see that. See the brick wall? Brick wall is definitively homogeneous because no matter where you put your bin, you see a pattern of bricks. However, there is a preferred direction, or at least there are directions where you can orient yourself left and right, and there's other directions where you go, okay, this is little stubby lengths and they're long lengths. So a brick wall is not isotropic, but is certainly homogeneous. And now this view of the the bullseye thing is certainly isotropic around the center, but is not homogeneous because you can go out to the edges of it and you see lines spreading, you don't see a line spreading out away from, say, the tip of one of these. You only see them spreading out from the center. So it's isotropic only around the center and is not homogeneous. Our trick is that we want both. We want both isotropy and homogeneity. So when we look at, we've determined that the cosmos seems to be homogeneous from our vantage point. And if we look out into the cosmos, we see that it looks the same in deep, deep, deep surveys in every direction, such as the Hubble Deep Field. We see roughly these things, this kind of thing, no matter which way we look. Now, if you take the cosmological principle, it says there's nothing special about our location in the universe, and that's been supported by the idea that we moved away from Ptolemy's place, where Ptolemy and Aristotle said the Earth is the center, that's the center of everything, and we're the center, we're the most important place. And then you went to Copernicus and said, no, we're off center. And then Galileo said, well, yeah, we're definitely off center. Kepler said, things move. And then Newton came along and said, it's just laws of physics, it's just stuff moving. And that began the idea that there's nothing special about our location in the universe. And then if you make measurements that demonstrate that you are isotropic around that point in the universe, it doesn't matter which one, any universe point, then you have combined isotropy around any point in the universe with the cosmological principle, and that means isotropy everywhere. So that means if you have isotropy everywhere, then it must be homogeneous everywhere. And therefore, anyone, anywhere in the universe sees things no matter which way they look. Now, what makes us think that this concept is that we're actually in nothing special about our location in the universe? And that arises from the idea of Newton's ideas about the laws of physics. We branch the idea from the concept of laws of physics, not from pictures. The pictures actually prove to us that things can be explained with laws of physics. So it's the explanation of the pictures using existing laws of physics. We don't have to make up new laws of physics in one direction to explain stuff over there in this direction, whereas if we look in this direction, we have to use different laws of physics because things seem to be behaving differently over there. It's not like we have to say, hey, in this direction of the sky, we have to use Newton's gravitational constant to be 100,000 times more than it is over here because things seem to be moving really fast over here in their orbits when they get in this part of the sky, if it's a planet, or distant galaxies in this direction of the sky seem to be moving really fast, then that's just what would be required if it was not isotropic. So when we think about it, the laws of physics must be the same because we see things that can easily be explained by the existing laws of physics, no matter which way we go. We also start with that as an assumption, as a very modern assumption, that the universe behaves according to laws and we can make our measurements where we can, not where we must. So there's a difference. So you can say, oh, this is where we must look in order to find this gravitational constant. No, we look where we can because that's where we can build a telescope. We look where we can because the Milky Way is not blocking that view. So that's what we mean by that, not where we must because, hey, if we want to see this law of physics, we look in this direction because that's the neat place over there. That's not the case. The laws of physics are the same everywhere. Therefore, there is nothing special about our location. Our location is the same laws of physics as any other location. And if you have isotropy plus that idea, then everything's the same across the entire universe. All right, let's take a little history lesson. Back in 1917, Albert Einstein was developing general relativity. And when he finished developing it, he said, well, what are the cosmological implications? What does this mean for the universe? And in 1917, pretty much everybody thought the Kapteyn model of the Milky Way was favored, where it was an island universe and that was the universe, and no one really knew about the distance to the spiral nebulae. Remember, that was a big, big, big argument, the argument of the Great Debate, which was about to come about in a few years. And so this was an important thing. The next thing is nobody really had good calibrations at the time of the period-luminosity relationship that Henrietta Leavitt was working on, but they're first just coming in by Hertzsprung, and Leavitt was like shaking her head saying, I could have done it. I could have been a contender, but it was blocked. Darn. So she was angry, but at least it got done, and she was the one who actually discovered the period-luminosity relationship for Cepheids in our libraries. So once these things those calibrations got done by everyone, then things could be progressed. Now Einstein, at 1917, because the universe was not known to be expanding, and the universe was known to only be the stars that were seen in the sky, that was the universe, he applied the cosmological principle to the general relativity, and he found, hey, this is kind of weird. Because gravity is here, and space-time is here, and stuff is here, the universe can't be static and unchanging. Stuff's got to move. And he found that space-time itself must either expand or contract. That's what he found. He said, this is really strange because there's stuff in the universe. The space-time itself must change. And it must either expand or contract. And that's the cosmological principle, meaning everything must everywhere expand or contract, no matter where you are. And so people said, oh, put down the chalk before you hurt yourself. And that can't be true because, hey, we're not seeing any expansion or contraction. So don't worry about it. I think you got something wrong there. You might want to go back. I mean, you're doing the math. We're doing the observations. We don't see anything. So Einstein went back and said, okay, great. So the universe is not expanding or contracting. Let's just do something. So what Einstein said was, he said, let's pop in a term into his equations. He said, okay, my equations clearly aren't complete, so I'm going to add this term called lambda. The lambda term is a cosmological constant that acts as a repulsive gravitational force. It is simply part of space. It is defined, arises straight out of empty space. It is a property of space-time itself. And it does things, it counters the effects of gravity, and it can even halt the motion of space-time and make it static. It can even do that. So at the time, there was no reason to introduce it other than the fact that the universe must be static. Because he said, well, we don't see any motion, and at the time people knew the Earth was a few billion years old, so if the universe is a few billion years old and those stars are there and the universe should be expanding and contracting and it's not, then the universe better be static. So here's a cosmological constant that does the job. Einstein was happy. He said, got it. Plugged it back in the equation, and then the cosmic expansion started to be getting discovered. Meanwhile, over in Arizona, Vesto Slipher at Lowell Observatory was measuring radial velocities of the bright nebulae, and this is about the same time Einstein was doing all this work. And he found that we discussed this before, we found that 21 of the 25 spirals had a systematic redshift. That meant that they had some apparent motion away from us. He could not calibrate the distance. He was like, wow, this is really weird, though. There's this really big motion. They seem to have large radial velocities, and when they do that, they redshift strongly. Oh, that's really weird. I don't know how far away they are, but they're far. This is kind of scary. And then Einstein thought he made a big old mistake, and this was when people really started getting very, very, very active. And so Einstein introduced this ad hoc cosmological constant to try to actually deal with the nature of the static universe. However, in 1920s, everything started falling down around really quickly. Theoretically, there was huge amounts of work that went into this because Einstein's theory of relativity was ripe for the picking. And Willem de Sitter, in the upper right, found that Einstein, you made a little error here, and said your cosmological constant made it static, but it's unstable. Sure, it's static, but it's a static just in the same way, perfectly balancing a pencil point on its tip. So any tiniest nudge, even a breath of wind will all of a sudden will make it tumble, and in fact that it will exponentially change now. So you might have a static universe, but it ain't gonna last long. Just like they say, so nice. Here's your static universe. Hope you can keep it. So basically is the idea. That was what de Sitter found. He's on the upper right. And then Friedmann and Lemaitre, Alexander Friedmann and Georges Lemaitre, who are the two on the right, lower right, showed that without a cosmological constant, if you get rid of that the general relativity seems to predict that the universe is actually expanding. And then Edwin Hubble in 1929, as we discovered, associated Vesto-Slipher's redshifts and others that he took with combining that with Henrietta Leavitt's work on Cepheid variables, and then being calibrated by Hertzsprung and others, and found that nearby galaxies not only had redshift, but that redshift had an order, and that ordering was the closer the galaxy was, the slower it was moving away from us. And the farther the galaxy was, the faster it was moving away from us. And there was the evidence that said the universe was expanding, and Einstein in the lower left said, say what? And said, this is going to be a problem. Okay, and he's called it my greatest blunder ever, as introducing that cosmological constant. Because gosh, we can't have a static universe. We can't have an unstable static universe. We have an expanding universe. So it's my original equations all along. Thanks, guys. I wish I'd known this 10 years before. I wouldn't have added it in. Thanks. Anyway, however, Einstein made, in order to do this, he had to actually assume homogeneity and isotropy in order to put the cosmological constant, in order to use general relativity to have any discussion about the nature of the cosmos. So he guessed that it was homogeneous and isotropic, and it was big. And modern observations do bear that out, as we discussed previously. Those galaxy surveys such as APM show that the distribution is basically the same everywhere on scales larger than about 100 megaparsecs. So there's the homogeneity. And maps of the cosmic background radiation. That's even more important because that's really old light that's traveled through, so it could get affected by anything on its trip to us. That cosmic background radiation, as well as pencil beam surveys, show that it looks the same in all directions, and that bears out the isotropic concept. So Einstein's guess was really right. He just added a cosmological constant in. All right. Now, funny thing is that good ideas don't really die, they just keep going. And the cosmological constant has reappeared recently in the last 20 or 30 years. Actually, it never really went away, but it reappeared as a result of observational needs. And so we see Einstein's equations of the field equations of relativity that show the curvature of spacetime, which is the Ricci tensor on the left with the letter R. The G is the metric by which we measure the spacetime, and the T indicates the tensor, or the stuff that's in the spacetime, and G is Newton's gravitational constant, and C is the speed of light. So the T is the tensor, is the field tensor that actually shows what the content of the universe is, and R is the curvature tensor, which shows how the universe is curved. So, and this is really fascinating. I know the relationship between what's in the universe and what its shape is given by this equation, which masks and is a summary, essentially, of many, many equations, at least 16 equations that summarize the nature of it. And the addition of the cosmological constant with lambda was important, because now we see it as a vacuum energy of space. And we consider this thing to be like the ground state of space. So we think of atoms like the hydrogen atom. The ground state of the hydrogen atom, the electron isn't in the proton. It orbits the proton in its lowest possible energy state. And that lowest possible energy state is given by the wavelength, the de Broglie wavelength of the electron. And that demands that the electron have a certain distance away from the proton. Now, there's still a potential between the two of them, meaning there's still an attractive potential, But the electron can't get any closer when it's bound as an atom. It cannot do so when it's bound as an atom. In just the same, in a similar, an analogic, not just the same, but in an analogous way, the universe has a minimum energy state with which it cannot get rid of. Just in the same way the electron can't get rid of that extra energy that it has by being this distance from the proton. Oh, it wants to be next to that proton, but it can't get any closer because it can't get any smaller. So I can't get smaller, so I can't get closer. They're trying to get together, but they can't. So the vacuum energy of space is essentially, I want to get to no energy. I'm trying to get to no energy, but I can't. I can't get rid of this energy. I never can. And so it's basically the lowest possible energy state of the universe. And as such, it actually adds pressure that pushes the universe apart, meaning that every particle piece of space has this energy density. It doesn't. So if you expand space, you don't dilute this. You simply make more of this because it is a property of space. So if space expands, there's more of this compared to everything else. And therefore, what's weird is that there's a lot of significant observational evidence that this stuff actually exists, which we'll talk about soon. In summary, we can remember that the concept of isotropy and homogeneity are well established. They say that we see, no matter which way we look in the cosmos, we see the same things. And if we were to travel to a distant galaxy 100 million light years away, they too would see the Hubble relationship with galaxies rushing away from us faster and faster the farther and farther they are. And they too would see similar, not exactly the same, of course, because it's a different place, but they would see the similar kinds of things when they bend things on larger size scales. And it doesn't matter how far you went. If you went 5 billion light years away from here and just used Doctor Who's TARDIS and jumped over there, you would not see anything significantly different, which is really fascinating. Now, which also implies that there are some galaxies that are rushing away so fast from us that some of them are currently rushing away from us faster than the speed of light because the expansion of space between us is great enough that that thing is pushing it away. So if even if we went to there, we would see the same thing. We wouldn't see everything rushing fast away around us at the speed of light. No, we would see, if we were 50 billion light years away, 50 billion light years away, we would see the same exact behavior no matter what. And that's what we mean by isotropy and homogeneity. And it also means the laws of physics are the same everywhere. And we will now use that in order to justify the 4 pillars of the Big Bang. We'll see you next time.